Hello, this evening I'm going to present you my bachelor thesis topic. Since it became more like a little more like a story and not some high science, I hope I'm not going to bore you to death. This method of the detection of meteors is based on radio propagation of radio waves, electric propagation of radio waves. And the subtitle refers to the fact that you don't really have to go anywhere and you don't need any special conditions to watch meteors. You can basically sit at home in your couch and watching as they are dying in the Earth's atmosphere from your couch. So it's a pretty old method. It's like from 50s or 60s from last century, from 20th century. So my task wasn't really like to bring something new, but more like test if this method is easy enough to do it at home and if it's cheap enough to do it at home. So it was very experimental work. First, I'm going to show you the illustration, which is basically the first page of my thesis, where I'm trying to present the whole story of the meteoric body from our solar system as I detected on my laptop. So I'm going to remind you what meteors or meteoroids are. We have a lot of comets in our solar system with very eccentric orbits. And as they are orbiting the sun, when they are close to the sun, they eject a lot of material from their core. And this material eventually is spread out around this comet orbit, and it follows its mother's body. The sizes of these particles are very different, but the thing you should know that very small particles can't really remain on this orbit because they are so small that because of the radiation pressure of the sun, they are basically pushed away out of our solar system. So what can happen when we have these orbits or trails, if you want? If there is a nice crossover with the Earth's orbit, these particles can die in Earth's atmosphere. We distinguish between two types of meteors. The first one you probably know and heard about a lot. Those are meteor showers, and then occur periodically every year in almost the same day, their peak and so on. And this is because we enter precisely this intensive stream of meteoric particles. And then it happens again next year and next year and next year. But we also have sporadic meteors that we can detect like every second, every hour, every day, every week. They don't really have a different origin. They are just very old. And that means that their orbits are already spread out through the solar system. So we can't see from where did they come from, what was their mother's body, or from what comet their origin is. So what is happening? Eventually, after successful crossover, the body of the meteor enters the Earth's atmosphere, and at the altitudes around 100 kilometers, the Earth's atmosphere is dense enough, so the high energy collisions can occur. Basically, what's happening here is adiabatic compression of the surrounding air. There is happening heating very rapidly, and the collisions lead to the very intense ionization. This ionization is happening in two main regions. First one is around the body of the meteor. Reflections of radio waves that can occur from this region, we call them head echoes. Since they are happening on the moving body, you can observe Doppler shift in your spectrum when you receive the signal. It's pretty cool. And on the other hand, as the body is moving through atmosphere, it's creating ionized trail, which is not really moving in the time. The small Doppler shift that you could observe possibly belongs to the fact that at these high altitudes are winds that can deform the trail and eventually break it to smaller pieces. So then the reflections you're going to detect are going to be from different times, from different areas with different density, and there is a really complex map that will lead to a lot of interference and so on. So what we need, as I was saying, that you can detect meteors through radio waves, you probably need some source of radio waves, and this source must have a very strong power, and also it has to be in a convenient location. For me, the most convenient location is this transmitter, which is part of the radio locator called RAF in France. And the convenient position is because it's far away enough, so the surface of the Earth is blocking the signal normally. But when some event occurs in these altitudes, the wave can be reflected, and so you can receive it in your receiver, which is far away. The most important information on this slide is the frequency of the transmitter that I'm going to use to create my receiver and eventually obtain the signals of reflected radio waves. This is how it looks like when you do a map of the radiation field of this transmitter at altitudes around 100 kilometers. So this is the area, this half ring is the area where the events will occur. I forgot to translate this map into English, but probably you see France. This is Czech Republic, this is where I'm from and where I was detecting. This is Germany. Then I have to build my receiver. The most important part from receiver is antenna, which is going to have some parameters that I will talk about later. Then the amplifier, because as the signal is scattered or reflected, it's going to be much fainter than the signal that is going from the transmitter. So you need to amplify that signal. Then there is this magic black box called software-defined radio. It looks like this. It's more like like 10 centimeters big. It looks like a flash drive. Costs around like 40 euros, and it's the most expensive thing I'm gonna use here. What is it doing? Basically, it works like an AD converter, which means that the analog wave is transformed into digital signal. So you get eventually numbers from your waves. It does a lot of Fourier transformation, and it was used originally it was used to receive digital TV signal or radio and so on. But then someone found out that it is very convenient to work with this dongle in a very wide spectrum, and that you can easily access the data from the dongle. So today it's a very popular dongle that radio amateurs use for detecting many radio signals of different frequency. This is the main part I must have designed. So what is antenna? The simplest antenna you can imagine is a dipole, which is basically a stick that is radiating into all directions except the one along its axis. But we don't want that. We know where the transmitter is, so we want our antenna to be directional. The most popular directional antenna is called Yagi antenna, or precisely Yagi-Uda antenna, since there were two people working on that. And I used 5 elements because it was convenient to move with antenna because I had to put it in a train and so on. So I really didn't need much of the many elements. And after like 5 elements, the power is not really that much different. But what is happening here? Directors are shorter than the dipole, and they are supporting radiation in forward direction, so this way. And a reflector, which is longer than the dipole, is basically blocking the signal from the back. So you shouldn't be interrupted by some other signals you don't want to detect. This is the antenna. So you here can imagine how is it big with comparison to me. As I was mentioning, the graph frequency, it's around 150 megahertz, which corresponds to the wavelength around 2 meters. And convenient length of the dipole is a half-wave dipole, which means that the power dipole, which you can see here, has around 1 meter. These are the graphs that I made in a software called Fornek 2. And they are not really nothing more than a map of how electromagnetic field of my antenna looks like. The first one on the left is like a horizontal cut through the field, and on the right is the vertical cut of the field. So the main thing you should notice here is that at 0 degrees in horizontal direction, there is going to be the most, like the highest power of the signal, as well as in 90 degrees in vertical cut. Then you don't really need to care about these red numbers because those are basically arbitrary units. The main thing is the shape of the lobe. Because as I'm going to show you, the horizontal one was pretty similar to the model, which I made on a computer. The vertical one is very different, and I will explain why. Why? Since the model is made in free space, there are no reflections from the Earth's surface. But of course, my measurements were done around the Earth, and this is finally what happened. The reflections from the surrounding objects and mainly the Earth's ground deform this pattern, so it looks pretty differently than the model predicts. Also, what I find really interesting is that my height is around the wavelength. So when I stand around my antenna that has vertical polarization, I basically work like a director or reflector based on my position to the antenna. So I'm disturbing my own signal, which is not really good. But fortunately, we don't really care about the vertical diagram because we want to know the direction where we want to look to, which is like in horizontal plane. Okay. Also, the fact is that the main parameter that we are going to use is the bandwidth that you can see with the dashed pink lines. The model predicted bandwidth around like 50 degrees, and I got smaller angle, which is good, since the smaller the angle, the stronger power you're going to receive. So you're going to receive more faint events, so more signal, like more meteors and so on. This is the map you have already seen, but I appended the radiation pattern of my antenna. You don't really care if it's radiation or like if it works like transmitter or like receiver, because the patterns due to the reciprocity, they are same. That's just a fact. So the mutual part of these graphs is the area where we are going to obtain the signal, if there are going to be some lucky events. You can see that I'm here, and I'm the direction of the antenna is towards the graph's transmitter. Sorry. And there is it. One of my first successful detections of meteor events. What you can see here on the horizontal axis, there is central frequency offset, which is basically how it differs from the frequency of the transmitter. So here, where is the 0 value, this is where the graph's frequency is. So this is the frequency I'm using to detect. These are high frequencies, these are lower frequencies. On vertical axis, we have local time. You don't really need to see these small numbers. I just put the difference between the two lines, so you could possibly imagine how long is the event that I detected, around like seconds, maybe, yeah. So the first typical thing you can see here is the head echo I was talking about, which has a very high Doppler shift from like 40 hertz to minus 200 hertz, 400 hertz, yeah. And what it means, basically, the radial velocity is changing when the meteor is moving. So here, the meteor is approaching the observer, then it passed the 0 Doppler shift, which means it's the distance to the reflecting point and to the transmitter is smallest. And then it's going far away from the observer again, so it's doing precisely. The second thing you can see here is the intensive signal in the middle with 0 Doppler shift, which corresponds to the trail echo I was talking about. And these small Doppler shifts you can see here, like in 10 hertz, corresponds to the half altitude winds. So also you can see smaller head echoes here without any trail echoes. That happens usually because to obtain trail echo, meteors have to have some specific geometry, which I'm not going to talk about, but you can ask me. This is the easiest concept you can get from obtaining the data. So basically, you're not looking at the single events like here, which I was showing you right now, but here, if events happen, you get one count. Then you count how many events occurred in 1 hour, and then you can see how is it changing in days. So what we can see in this picture is that around 6 a.m. every day, there are the maximums of counts, and around 6 p.m. there are the minimums of counts. So why is it happening? This belongs to the sporadic meteors, and it's because as the Earth is moving around the Sun on its orbit, at every second it is heading towards the direction we called apex. And as it's moving in the solar system, where are the particles that are burning in our atmosphere, their relative velocity is bigger in forward direction of the Earth, and their relative velocity is smaller in back direction. So wherever you are at 6 a.m., you're going to detect meteors from the bigger value from in 1 hour than you would detect in the evening. This is the same effect that happens when you drive the car and it's raining and you're approaching the raindrops. So you will detect more raindrops in your forward window and less on your background. So this is the same thing, but with the large time scale. So you can see it's from December last year, but we can't really see any significant diurnal variation as in the picture before. And this is because around 14th of December, something is happening, And that something is the peak of the meteor shower called Geminids. So you can detect very large peak here around 6 a.m. On 14th of December. And this peak is rescaling all of these variations we could see. So to obtain the more real picture of daily diurnal variation of meteors, I had to cut out these 2 days. And now what we see here, precisely the same thing as here, that at 6 a.m. there are like 2 times or 3 times more events than in the evening. This is also the good indicator of the fact that we were probably detecting meteors, because noise or some other signals wouldn't have this variation. This is typical for meteors. And also the maximum of Geminids is also a pretty good indicator. As we look at individual events, we can see profiles that are called power profiles or diffusion profiles, and they correspond to the different density of plasma around meteor or of the trail that is created from plasma. If the density is low, we call these meteors underdense meteors, and that means that the plasma is lower than the critical density, and each particle of the trail is scattering the wave, and it's very faint, and then the electrons are diffusing into the surrounding air, and it happens very quickly. So there is exponential decay, and it's on a scale of microseconds. But on the other hand, you can have overdense meteor, which is above critical density, and as long as the plasma of this meteor has the value that exceeds this critical density, it's going to be pretty constant until the cone is spread out enough that the critical density is decreasing again. So the exponential decay will happen as it happened in the first picture. This corresponds, of course, to the more bigger and massive meteors, and this to the faint meteors. And as you can see, the scale of overdense meteors is more in seconds, and also can be in if it's a big bolide, it can occur for 10 seconds or 20 seconds and so on, but it's very rare. What we can do with this? This was more like an experiment, what you can do with one antenna, because as I was telling you, my greatest task was to do it DIY by myself at my home. So the scientific data wasn't really before. I didn't obtain any distribution or some interesting Doppler shifts or so on. But I decided that if I fit these profiles that I got, these are not mine, these are from the Ramses, they are just to illustrate the 2 different events. But if I fit, or I put exponential function here in my signals, which looks like that, I could get this value, which is the coefficient of the exponential decay. And from this value, I can obtain the angle, which corresponds to the half of the scattering angle. And then I could potentially very approximately and very roughly locate where was the reflecting point. So where was the meteor when I was detecting it in my laptop. So this is transmitter, this is receiver, this is reflecting point, so where the reflection occurred. This is the same point, but on the Earth's surface, his projection. The red distances can be measured in Google Maps or anywhere, even with the spherical correction, so it's more precise. The H is the altitude, which we estimate for 100 kilometers, because we know it's going to happen somewhere here. And that's it, because these black distances you can you can calculate with simple geometry, precisely through cosine rule. And then you obtain these angles. And I managed to locate the meteors to this area, which is not weird because it's the closest region to my receiver. So I was receiving probably the strongest signal from this area since transmitter is here. And yeah, so if you would like to locate it more precisely, like precisely this point or like anywhere, you would need many antennas. And this is what Bolidozor does, or any other like network of these radio amateur station. It's spread out through the world, and they doing precisely this because you have a lot of antennas, and through triangulation and through interferation you can get the precise location of the meteor. So as I was talking about, my task was to build antenna and find out if it was easy and if it is cheap. So yeah, everyone can do this at home. The most expensive was the dongle, which I obtained from my supervisor, so I paid nothing. And the material for the antenna I had at home. This doesn't happen to anyone, I understand, but I had it. So I made antenna, then I verified its parameters, if it's good enough for our purpose for detecting this meteor reflection. Then I was able to see the Gemini's maximum, or the peak, if you want, which speaks pretty surely that I was detecting meteors, also through the diurnal variation and so on. And I also detected both kinds of reflection from different ionized regions, as I have mentioned, head echoes and trail echoes, and distinguish between two possible profiles. And then I made a very rough localization attempt. And that's it.